Chapter P is a preliminary chapter that is just an overview of a bunch of different things that we will be talking about throughout the year. We're going to talk very briefly about certain topics, kind of talk about things that we'll visit, not until some of it until second semester. So it's just kind of an overview of what all is involved in the course. Statistics, by definition, is the science of learning from data. The essence of the majority of this course, which we will be talking about second semester, is inferential statistics. In inferential statistics, we want to talk about how we can take targeted samples and use data from those samples to describe a population. Population is simply a large group of individuals. Sample then would be a small group of individuals. Many times we want to make some inferences about the entire population of the United States of America, and it's very difficult, obviously, to talk to every single individual to get data, so we take a targeted sample from that population of all United States citizens and use that sample data then to make predictions about how we believe the population is going to behave. So another example of the difference between sample and population. All AP Statistics students versus AP Statistics students only at Hananiga. The students at Hananiga represent a smaller subgroup of the overall population of all students that are taking AP Statistics. All McDonald's in the US versus all the McDonald's in Rockford. McDonald's in Rockford would be a smaller sample of the entire population of all the McDonald's in the USA. The second semester is when we will get into our inferential statistics, and inferential statistics uses sample data to make inferences about populations. So how do we get good data? Okay, and one thing you're going to learn throughout this year is that just because you have a data set does not mean it's a good data set, and we'll talk about how we can take safeguards when we are taking our samples so that we do get a good data set. Okay, but one way that we can get data is through a survey. When we do a survey, we would want to select a sample to represent the larger population that we are looking for information about. We then would want to ask those individuals in the sample some questions, record their responses, and then use that sample to draw conclusions about the population. So a survey is one way that we could go about getting data. The second way that we can obtain data is through an observational study. Observational study, just as the name says, you simply observe individuals and you measure variables of interest, but you do not attempt to influence the responses. So an observational study, you just simply observe. It could be somebody coming into this classroom, sitting at the back of the classroom, and they want some data on how many students are participating on average in daily lessons. They would simply sit in the back of the room. Every time a student participated with an answer or some additional information, they would make a tally mark and count how many individuals participated on that certain day, but they would not deliberately influence whether or not a person responds. An experiment now deliberately do something or give them a treatment, and this word treatment is going to be the key. This is really what separates an observational study from an experiment. In an experiment, you give them a treatment, and then you observe their responses. So in an observational study, the way you're going to know the difference between the two in an observational study, there is no treatment. In an experiment, there is a treatment. And how you get data is very important. Conclusions based on data are only as good as the data they're based on. Poorly generated data gives meaningless results. So you can apply all the fancy statistical techniques you want to a data set, But if the data is a bad data set, it doesn't matter what statistics you use on it, you're going to have meaningless results. Looking at our first example here. One study of cell phones and the risk of brain cancer looked at a group of 469 people who have brain cancer. The investigators matched each cancer patient with a person of the same age, sex, and race who did not have brain cancer, then asked about their use of cell phones. The result? Our data suggests that the use of a handheld cellular phones is not associated with the risk of brain cancer. So question A, is this an observational study or an experiment? Justify your answer. This is an observational study. The reason it's an observational study, remember you're going to be able to identify the difference in the two on whether or not there is a treatment. In this case, there is no treatment given. Letter B. Based on this study, would you conclude that cell phones do not increase the risk of brain cancer? Why or why not? This is something that we will get into later on. You cannot establish cause and effect relationships from observational studies. So based on this study, would you conclude that cell phones do not increase the risk of brain cancer? No, you can't do that. And the reason is because cause and effect relationships cannot be based on observational studies. Number 4, is this a survey, an experiment, or an observational study? What is the base? Explain your answer choices. So for each of these, you're going to identify it as being a survey, an experiment, or observational study. Then you are going to justify why you believe it is whatever you pick. So in this case, are people generally satisfied with how things are going in the country right now? Well, this would best be measured by a survey. Who usually does surveys? Well, if you look at the news, newspapers, go on the internet, usually surveys are done by polling agencies such as Gallup or AP or ABC, NBC, Fox News, CNN, something like that, that has a lot of practice in doing polls or surveys. So in this case, it's a survey, and this would be conducted by a polling agency. Letter B. Do college students learn basic accounting better in a classroom or using an online course? This would be an example where we would want to do an experiment. And in an experiment, what we do, this is a keyword that you're going to see anytime you're talking about experiments, is you would randomly assign half of the students to the classroom and the other half to the online course. Then at the end of the class, all students would take the same post-test. We could then compare results on the post-test for the students that took the online course versus those that were assigned to the classroom, and compare results to see which students learned the most. Letter C, how long do your teachers wait on average after they ask the class a question? This would be an observational study. The way this question is asked, you're not interested in changing or influencing how long a teacher waits after they ask a question. You just want to know typically how long do each of your teachers. That would be done through a simple observational study where you would have somebody sit in the back of the classroom, teacher asks a question, they start a stopwatch. As soon as a student answers the question, stop the stopwatch, see how long the teacher waits before a question is answered. Making sense of data. Individuals are the objects described by a set of data. Variable is any characteristic of that individual. 4 key questions you should ask about data sets: who, what, why, when, where, and by whom. Okay, you're not going to answer these each time, but a lot of times you need to know the background of certain results that are given to you, whether it be a survey, an experiment. You need to know who are the individuals being described by the data and how many are participating. You need to know what are the variables and the units of measure. Why was the data gathered? Okay, for instance, if I am a CEO of a drug company and I believe that I have this new drug that is going to prevent heart disease, and I solicit somebody in my company to do an experiment with this new drug, I obviously am going to benefit on the results of that survey. Okay, so the survey results could be biased, or we could do something to attempt to influence those so that it makes our company look good, and then I can make money off of selling this new drug. So always know why or who has an interest in why the data was gathered. Different types of variables that we can measure. Categorical variable places an individual into one of several groups or categories. Quantitative variables takes numerical values for which mathematical operations make sense. Sorry about the bottom part being cut off here. Bottom part that is cut off says mathematical operations make sense. So take numerical values for which mathematical operations make sense. So looking at some different types of graphs. A distribution tells what values a variable takes and how often it takes these values. Exploratory data analysis, sometimes abbreviated EDA. Exploratory data analysis is examining data to describe their main features. We have 2 different types of graphs down here. First one on the left is a simple bar graph for categorical variables. We have regions of the United States divided up in the Northeast, Midwest, South, and West. This is simply a side-by-side bar graph. Next, we have a dot plot. Dot plot for the number of goals scored by the U.S. women's soccer team in 2004. You can see that the number of matches represented here would be the total number of dots. They scored 0 goals in 1 match. They scored 1 goal in 2, 4, 6, 8 matches. They scored 2 goals in 6 matches, and so on. This again is an example of a dot plot. Next example. Data from a medical study contain values of many variables for each of the people who were subjects of the study. Which of the following variables are categorical and which are quantitative? The gender of a person, whether they are male or female, we're putting them into a category of either being male or female, so that is clearly a categorical variable. Age in years. Well, age is represented by numbers, which have a definite meaning. So that is a quantitative variable. Your race, whether you're Asian, black, white, or other, putting you into a category, is a categorical variable. Whether or not you smoke, categorical variable, you would answer either yes or no. Systolic blood pressure, measured in millimeters of mercury. That would be a numeric value, so that's quantitative. And level of calcium in the blood in micrograms per milliliter is also a quantitative. Another area that we'll talk about, but not as much as what a lot of people think. A lot of times people think if you're taking statistics, there's going to be a ton of probability in it. Okay, in introductory statistics courses, there's really very little probability. Probability is simply what are the chances that a certain event will happen. The important thing on probability, which when we get to it, we'll be talking about over and over again, is that chance behavior is not predictable in the short run, but is predictable in the long run. Okay, the graph here shows the flipping of coins. Number of tosses are along the bottom here. The proportion of times that a coin comes up heads is up the side. We know that when we flip a coin, we have a 50-50 chance, or it should come up heads about 0.5 out of 1. So in this case, if our proportion is 0.5, that means half the time it's coming up heads. We can see in the short run here, up through 10 tosses, sometimes the proportion is quite a bit less than 0.5. Sometimes it is more than 0.5. But we can see as the number of tosses increase, and we get closer and closer and closer to that line of 0.5, meaning that it's heads half the time, tails half the time. And that's a good example of how chance behavior is not predictable in the short run, but is predictable in the long run. In other words, if I flip a coin 3 times, okay, it's not going to, or I should say 4 times, it's not always going to come up heads twice and tails twice. In fact, it would not be unreasonable for me to get 4 straight heads, okay, because probability is predictable in the long run, not necessarily the short run. Statistical inference, which is the most interesting part of the class, is drawing conclusions from a data set. And here's an example of things that we will be doing. Experiments and inference. Most women who reach middle age have regular mammograms to detect breast cancer. Do mammograms really reduce the risk of dying of breast cancer? To seek answers, doctors rely on randomized clinical trials that compare different ways of screening for breast cancer. We will see later that the data from randomized comparative experiments are the gold standard. The conclusion from 13 such trials is that mammograms reduce the risk of death in women aged 50 to 64 by 26%. On average, then, women who have regular mammograms are less likely to die of breast cancer. Of course, the results are different for different women. Some women who have mammograms every year die of breast cancer, and some who never have mammograms live to 100 and die when they crash their motorcycles. Okay, this book, as in most statistics books, will have little what are supposed to be humorous tidbits like that in there. You can kind of just ignore it as far as the statistical thinking. If you find it funny, feel free to laugh. In spite of this individual variation, the results of the 13 clinical trials provide convincing evidence that women who have mammograms are less likely to die from breast cancer. That's because probability tells us that the large difference in death rates between women who had regular mammograms and those who didn't was unlikely to have occurred by chance. Can we be sure that mammograms reduce the risk on average? No, we can't be sure because variation is everywhere. And that's going to be the key when you do an experiment, is to try to reduce that variation so we can be more confident in our results. We cannot be certain about our conclusion because of variation. However, statistics helps us better understand variation so we can make reasonable conclusions. Statistics gives us language for talking about uncertainty that is used and understood by statistically literate people everywhere. In the case of mammograms, the doctors use the language to tell us that mammography reduces the risk of dying of breast cancer by 26%. A 95% confidence interval showed that that percent is somewhere between 17 and 34, which means that this survey, they are 95% confident in the method they used, that the risk of dying of breast cancer is between 17 and 34% less when you receive regular mammograms. According to Arthur Nielsen, head of the country's largest market research firm, that 26% is a shorthand for the range that describes our actual knowledge of the underlying condition. The range is 17 to 34%, and we are 95% confident that the true percent lies in that range. You will soon learn how to understand this language. We can't escape variation and uncertainty. Learning statistics enables us to deal more effectively with these realities. So looking at some simple probability here. What is the probability of getting a 6 if you roll a fair-sided die? Explain carefully what your answer means. Well, if we're rolling a 6-sided die, it's the numbers 1 through 6. I have a 1 in 6 chance of rolling a 6. So what does this mean? It means, and these are the key words, in the long run, a 6 will come up about 1/6 of the time when rolling a die. An August 2004 Gallup poll asked 439 teens aged 13 to 17 whether they thought young people should abstain from sex until marriage. 56% said yes. If Gallup had asked all teens aged 13 to 17 this question, would exactly 56% have said yes? Explain. No, it would not be. Could it be exactly 56%? Yes. But are we guaranteed that it's going to be? No. Why are we not guaranteed that? Because remember, the key word that we're going to always talk about is variation. And there is variation from sample to sample. In this sample, 48% of the boys and 64% of the girls said yes. Are you convinced that a higher percent of girls than boys aged 13 to 17 feel that way? Why or why not? Okay, well, the difference between 64 and 48 is pretty significant. 16% is quite a bit. Okay, if this was 50% and 48%, well, now we may not be convinced that the two respondents were different. But in this case, because there was a large difference, we could say yes. Number one, our sample size was 439, so that's a large sample. So the sample size was relatively large. And a difference of 16% is rather large. Problem 24. Late in 2004, baseball superstar Barry Bonds admitted using creams and ointments that contained steroids. Bonds said he didn't know that these substances contained steroids. A Gallup poll asked a random sample of U.S. adults whether they thought Bonds was telling the truth. 42% said probably not. 33% said definitely not. Why did Gallup survey a random sample of U.S. adults rather than a sample of people attending a major league baseball game? Well, first of all, if they were interested in the opinions of all U.S. adults, you have different types of people that go to a baseball game than don't go. So if we only went to a baseball game and surveyed people, we're going to have a different target population than if we want to know about the entire U.S. population. So because they were interested in the opinion of all U.S. adults, and not just those attending Major League Baseball games. Part B, if Gallup had surveyed all U.S. adults instead of the sample, about what percent of the responses would be probably not and definitely not? Well, we could estimate that those that would say probably not would be 42%, and those that said definitely not would be about 33%. And why? Well, even though there's variation from sample to sample, this is the best estimate of the population parameter. Part C, can we conclude based on these results that Barry Bonds is lying? Why or why not? No, we can't make that conclusion. Okay, why can we not make that conclusion? First of all, or the main reason is because this is simply opinions of U.S. adults. So we could probably make the conclusion that most U.S. adults think he's lying, but just because their opinion is that he's lying doesn't mean in reality that he is.